Dear students, today we will discuss about standalone photovoltaic system, its design approach, and before we start today's discussion, let us summarize what we have discussed in the last class. Okay? So, we are mostly discussing about PV modules, its classification, effect of shadowing, packing factor and module efficiency, ways of maximization of PV module performance, maximum power point tracking, and possible strategies for operation of MPPT, PV arrays and PV systems. So, knowledge of this PV module is very important while selecting a best module for standalone PV system applications. So, without delay, let us start our today's discussion. So, mostly today we will be covering about the components of standalone PV system and system design approach. So, what is standalone system? The standalone system is a solar PV system that produces electrical power to charge banks of batteries during the day for use at night. A standalone small scale PV system employs rechargeable batteries to store energy, which is supplied by PV panels or arrays. The standalone PV systems are ideal for remote areas where other power sources are either impractical or unavailable to provide power for lighting and other uses. So, different components of a PV systems are PV modules, which is the primary component, then mounting structures, then charge controller, battery, inverter, then DC-DC converter and cables. So, as you can see here in the figure, so PV modules are installed on the rooftop. Okay? So, this PV array converts sunlight into direct current, right? And we need to have a charge controller to protect the battery from the overcharging, right? So, we need battery banks which stores energy produced by the PV arrays. Okay? And then if we have AC load or alternating current load, then we have to convert this direct current which is generated by PV arrays to the alternating current by an inverter, and we need power meter and an electric grid sometimes, or sometimes we can use the generated energy locally, right. So, what you can see here, there are two configurations of a standalone system. So, first configuration where there is no charge controller and battery bank, and the second configurations will have charge controller and then battery banks. Okay? So, here this is an example of lifting water from the ground and storing in a reservoir, and then finally we can use this reserve water for irrigation applications, okay, because in irrigation we need huge amount of water. Okay. This is something like solar powered water pumping systems which is used in irrigation. And these configurations what we have shown, there are many modules are connected and we will have a charge controller to protect these batteries for overcharging. Okay. There are batteries here. So, we will study how many batteries are required for a single applications, and we need to have inverter to convert this DC current to AC current. Okay. So, if load is DC, then straight away you can use from the charge controller. Okay. So, these are the two extensively used configurations. Okay. So, this is somewhat complex, okay, where we have many components, and this is a very simple configurations. One more configurations we have, suppose in a single day we do not have enough sunlight, okay, then amount of energy generation by this PV module will be very less. Okay. Then under that conditions, in order to meet the demand, then we need some kind of backup system. Okay. So, here what we have shown, this is a generator backup system, and this is coupled with that existing connections, right, so that we can meet the demand during those cloudy days or rainy days. Okay. So, primarily what we have understood, there are components like solar PV which convert sunlight to electrical energy, and we need to have a surge controller, okay, to protect these batteries from overcharging. Okay. And if we have AC load, then of course, we need an inverter to convert direct current to alternating current, and sometimes there are some loads where we need only DC current. So, under that conditions we do not need inverter. Okay. So, we will study one by one those components which constitute a standalone PV systems. So, let us first study the batteries. Okay. So, batteries are electrochemical devices that converts chemical energy into electrical energy. Okay. So, there are two kinds of batteries normally used, primary batteries and secondary batteries. What is primary batteries? Which convert chemical energy to electrical energy irreversibly. Okay. So, for example, we have zinc carbon and alkaline batteries are primary batteries. Okay. We cannot recharge again and again, but in case of secondary batteries, that is called rechargeable batteries which convert chemical energy to electrical energy reversibly. Okay. So, example is something like lead acid batteries, lithium ion batteries. Okay. So, these are some of the examples, right. So, if you look into this chart is known as Ragon chart, which is used for comparison of different batteries. So, you can see the position of lead acid batteries is here, and lithium ion batteries and lithium polymer batteries are here. Okay. So, in the vertical axis it shows volumetric energy density, and in the horizontal axis it shows gravimetric energy density. Okay. And gravimetric energy density represents watt hour per kg, and volumetric energy density represents watt hour per liter. Okay. So, what does it mean? So, gravimetric energy density is the amount of energy stored per unit mass of the battery. Okay. And volumetric energy density is the amount of energy stored per unit volume of the battery. Okay. Already we have defined those units, and as you can see, if volumetric efficiency increases, what does it mean? Higher the volumetric energy density, the lighter the battery can be. That is why now this lithium ion and lithium polymer batteries are lighter than lead acid batteries, and higher the volumetric energy density, smaller the battery size. At the same time, the size of these lead acid batteries are higher compared to lithium ion batteries. Okay, as you can see here, right. So, this chart is normally used to compare character of the different batteries. Now, let us learn something about lead acid batteries, which is the oldest batteries, and technology is quite mature. A typical battery is composed of several individual cells, of which each has a nominal voltage of 2 volt. Okay. So, what happens if we look for 12 volt battery, then how many cells are required? It will be 6 cells, right. Each cells will give 2 volt. Okay. So, for a cell it works something like this. Okay. 2 metal electrode will be there and electrolyte will be there. So, electrolyte is nothing but diluted sulfuric acid, and this electrode contains grid shaped lead carrier and porous active material. Okay. So, this porous active material has a sponge like structure which provides sufficient surface area for the electrochemical reaction. Okay. Normally, this Pb in one electrode is in negative, and then PbO2, so lead oxide is positive. Okay. When an external load is connected, electron will flow from negative to the positive terminal. Okay. So, when the battery is discharged, the electron flow from negative to the positive electrode through the external circuit. Okay. which causing a chemical reaction between the plates and the electrolyte. Okay. These are the electrolytes here and these are the plates. Okay. This forward reaction also depletes the electrolyte, affecting the state of the charge. Okay. So, SOC, we will define what is SOC. So, it affects the state of the charge. Okay. And when the battery is recharged, the flow of electron is reversed, of course, as the external circuit does not have a load, okay, but a source with a voltage higher than that of the battery enables the reverse reaction. Okay. So, this external source is nothing but solar source. Okay. So, this is also known as solar battery, because lead acid batteries are used in solar research. Okay. So, overall reaction will be something like this. So, lead and the lead oxide reacts with sulfuric acid, and then we will get PbSO4 and then H2O, and each cell will give about 2 volt of energy generation. Okay. So, this is how a lead acid battery works. And if we talk about lithium ion and lithium ion polymer batteries, as we can see from the Ragon charts, that high energy density has made them favorable technology for lightweight storage applications like mobile communications. Okay. And these technologies still suffer from high cost and low maturity. Okay. So, this is the reason why this cannot be used in solar research or solar photovoltaic applications. So, as you can see, there are many applications of lithium ion and lithium polymer batteries. So, e-bikes are there, scooters are there, gardening tools, tablets, mobile phone, everywhere these lithium ion batteries are used. So, let us learn something very important aspects of batteries. These are called battery parameters. So, voltage, capacity, then energy capacity of the battery, then SOC, and then depth of discharge, all those parameters. So, start with voltage. The voltage at that battery is rated is the nominal voltage at which the battery is supposed to operate. The solar batteries or say lead acid grid plate batteries are usually rated at 12 volt, 24 volt or 48 volt. That is what I said, the number of cells required, if single cell is giving 2 volt, then number of cells required to get 12 volt will be 6 cells. Okay. So, that has to be connected in series. And capacity refers to the amount of charge that the battery can deliver at the rated voltage. Okay. So, this rated voltage is very, very important. This rated voltage is nothing but nominal voltage, right. The capacity is directly proportional to the amount of electrode material in the battery. That is why smaller size battery, if we compare with the bigger size batteries, then what will happen? The smaller size batteries capacities will be lower compared to larger size batteries. Okay. But the voltage will be constant. The voltage of the cell is more chemistry based, while the capacity is more based on the quantity of the active material used, which is very, very important. Okay. The capacity, which is also represented as C bat, okay, is measured in ampere hour. Okay. So, charge usually is measured in coulomb, that we all of us know. Ampere second. Electric current is defined as the rate of flow of electric charge. Ampere hour is another unit of charge, right. Since 1 coulomb is 1 ampere second, right. And if we multiply this with 3600, then it will become 1 ampere hour, which is nothing but 3600 coulomb, right. Also, we are interested to calculate the energy capacity of a battery. So, how to get it? So, energy capacity of the battery can be calculated by multiplying this C bat with this rated voltage. Okay. So, if we know this C bat and rated voltage, if we multiply, what we will get is a energy capacity of a battery, which is very, very important, and it is represented in terms of watt hour. Okay? So, capacity is measured in ampere hour, and energy capacity of the battery is measured in watt hour, right. Now, one more very important parameter called C rate. Okay? This C rate is a measure of the rate of discharge of the battery relative to its capacity, right. So, it is also defined as the multiple of the current over the discharge current that the battery can sustain over 1 hour. Okay? Suppose, for example, a brand new battery with 10 ampere hour capacity, already we have defined what is capacity, theoretically can deliver 1 ampere current for 10 hours at room temperature. Okay? That you should keep in mind. So, a brand new battery with 10 ampere hour capacity theoretically can provide 1 ampere hour current for 10 hours at room temperature. Okay? It is related to temperature at which the system will operate. Okay? For example, C rate of 1 for 10 ampere hour battery corresponds to a discharge current of 10 ampere over 1 hour. Okay? So, same battery if we consider for the case 2, like C rate of 2 for the same battery would correspond to a discharge current of 20 ampere over half an hour. Okay? And then one more example, if we take C rate of 0.5 implies a discharge current of 5 ampere over 2 hours. Okay? In general, it can be said that C rate of n corresponds to the battery getting fully discharged in 1 by n hours, irrespective of the battery capacity. Okay? This we should keep in mind. Okay? And this example will be very much helpful to understand how C rate is defined. Also, we must know what is battery efficiency. Battery efficiency also sometimes known as round trip efficiency. Round trip efficiency. So, for any storage system, we must know what is round trip efficiency. Okay? Suppose, for example, if we have to say pump some amount of energy, maybe 10 kilowatt hour of energy we are pumping, okay, in a charging process, and maybe 8 kilowatt hour of energy we are retrieving in the discharge process. Then what will be the round trip efficiency? It will be 80%. Okay? So, 8 by 10 will be 80%. So, in case of battery, so this round trip efficiency is connected with voltaic efficiency and Coulombic efficiency. Then finally, we will have a combined efficiency, okay, that is called battery efficiency, and that take care of this round trip efficiency, right. So, what is voltaic efficiency? The ratio of the average discharging voltage to the average charging voltage. Okay. So, we know the discharging voltage and charging voltage, that ratio will give you voltaic efficiency. Okay. And second efficiency is Coulombic efficiency, okay, or it is also known as Faraday efficiency, which is the ratio of the total charge got out of the battery to the total charge put into the battery over a full charge cycle. Okay. And this is defined as Q discharge by Q charge. Okay. So, if we combine both the efficiency, what we will get is a battery efficiency. So, if we multiply these two, then what we will have is a battery efficiency. So, this battery efficiency is considered for comparison of different storage devices, okay, and it includes all the effects like chemical and electrical occurring in the battery, right. So, these efficiencies are important to evaluating a battery. Also, we must know what is the state of charge of a battery, which is defined as the percentage of the battery capacity available for discharge. Okay. So, what we see in the mobile phone, what we use nowadays, so it shows like 80%, 70%, batteries are remaining in the battery, that means that SOC is 70%. Okay? So, SOC is equal to E bat, energy of the battery, C bat, capacity of the battery, multiplied by rated voltage. Okay? So, for example, a 10 ampere hour rated battery that has been drained by 2 ampere hours is said to have a SOC of 80%. Okay? So, this is something like 10 minus 2 divided by 10, okay? It will be 80%. And also one more parameter we must know when we talk about battery parameter is called depth of discharge. So, it is defined as the percentage of battery capacity that has been discharged. Okay? So, it is represented by DOD, which is C bat, capacity of the battery multiplied by rated voltage minus energy of the battery divided by C bat multiplied by V. Okay? So, same problem if we have to define in terms of DOD, it is something like a 10 ampere hour battery that has been drained by 2 ampere hours has a DOD of 20%. Okay? So, this SOC and DOD, okay, state of charge and depth of discharge are complementary to each other. We should keep in mind. Also, we need to define one more terminology called cycle lifetime, okay, which is defined as the number of charging and discharging cycles after the battery capacity drops below 80% of the nominal value. Okay? So, this battery cycle again depends on the operating temperature, right. So, colder operating temperature means longer cycle lifetimes. Okay? And the smaller the DOD means depth of discharge, the higher the cycle lifetime. Okay? So, these are important observations and how the cycle lives are affected by temperature and DOD. And how temperature affects the battery life. So, this battery life is increased at lower temperature. Okay? If you can keep at low temperature or room temperature, then battery life is expected to be higher, and lower the temperature, lower the battery capacity again. Okay? So, what happens? The chemicals in the battery are more active at a higher temperature, okay? And the increased chemical activity leads to increased battery capacity. Okay? So, by increasing the temperature we can increase the capacity of the battery, but no, if increase more than a specified value, then it will give a detrimental effect to the battery health. Okay? And also we have aging. Okay? So, major cause for aging of the battery is sulfation. So, what is sulfation? So, if a battery is insufficiently recharged after being discharged, okay? Suppose if I am using a mobile phone, if it is no 50% charge is available or SOC is 50% and we are charging it for say 80%, 50%, 80% and then stop it, again we use it for 80%, 90%. So, that way if we make, then no, we are reducing the efficiency because of this sulfate crystal generations. Okay? So, sulfate crystals start to grow, which cannot be completely transformed back into lead or lead oxide. Okay? So, thus battery slowly loses its active material mass and hence its discharge capacity. Okay? And corrosion is also one of the problems, and because of this corrosion electrolytes may dry out, and at a higher charging voltage, if the battery is charged at very high voltage, gassing can occur. Okay? So, gas will be generated, which results in the loss of water. As you can see in the overall reactions, water will be there at the product side. So, that water losses will be there. Okay? So, thus demineralized water should be used to refill battery for time to time. That is why we have to buy demineralized water, okay, to be used in those lead acid batteries for proper functioning. Now, let us discuss something about charge controller, which plays a key role in a standalone system where battery is involved. Okay? So, charge controllers are used in PV system that use batteries. Okay? So, it is very important to charge and discharge batteries at right voltage and current levels in order to ensure the longer battery lifetime. Okay. A battery is an electrochemical device that requires small over potential to be charged, that we should keep in mind. So, we need some kind of over potential for charging. The amount of current sent to the battery by PV array and the current flowing through the battery. So, if we consider it is a battery, the amount of current flows from the PV and then going out from the battery. Okay. So, this will go to maybe inverter. Okay. So, I am talking about this and this, okay, this current and this current. So, this is for discharge and this is for charging, have to be within the well defined limit for proper functioning of a battery. So, that is very, very important. This current, no charging current and no discharge current has to be at the proper level as described by manufacturer. Okay. This PV array corresponds dynamically to ambient conditions like irradiance, temperature and other factors like shading, what we have discussed in the last class. So, these are very, very important things, because every time we are not going to get the same solar irradiance. Okay. So, it will vary with time, okay. And also when solar radiation increases, then temperature also increases. So, we need to think many parameters for proper functioning of a solar PV standalone system. Okay. So, this direct coupling of battery to the PV array and the load is detrimental to the battery lifetime. Okay. Therefore, a device is needed that controls the current flowing between the battery and the PV array and the load, and that ensures that the electrical parameters present at the battery are kept within the specifications given by the battery manufacturer. So, that is the function of a charge controller. Let us learn more in depth about this charge controller, how it works in a PV system. So, when the sun is shining at peak hours during summer, the generated PV power excess the load. Okay? The excess energy is sent to the battery. When the battery is fully charged and the PV array is still connected to the battery might overcharge, okay, which may cause several problems like gas formation, capacity loss and overheating. Okay. So, this is one concern, but if we have a proper charge controller which plays a vital role by decoupling the PV array from the battery, right. This is how this charge controller is useful in maintaining the proper life of a battery in standalone PV system. So, during severe winter, and now second case is when solar irradiation is very, very low and battery is heavily discharged as the load exceed the power generated by the PV array. Okay. So, over discharging the battery has a detrimental effect on the life cycle. Okay. The charge controller prevent the battery from being over discharged by disconnecting the battery from the load. Okay. This is the second function of this charge controller. Okay. Now, this PV array will have its MPPT, maximum power point, at different levels. As you can understand, if we remember this IV characteristics curve. Okay. So, this is maybe one irradiance and this may be other irradiance value. Okay. So, this value will change as irradiance will change, right. This is what it is mentioned. So, PV array will have its P maximum power point. Okay. So, this is MPPT at different levels based on the temperature and irradiance conditions. Hence, the charge controller needs to perform appropriate voltage regulation to ensure the battery operates in the specified voltage range, while the PV array is operating at maximum power point. Okay. So, of course, these modern charge controllers often have an MPPT tracker integrated. Okay. So, if this MPPT is integrated, then it is not a problem, it will operate at the maximum power point. So, a charge controller that contains a proper current regulation is also able to control the C rate. Okay. So, this charge controller also controls this C rate. Okay. finally this surge controller can impose the limits on the maximal current flowing into and from the battery. Okay. So, if we consider this is PV array, okay, this is PV array, and we have battery, and then we have maybe inverter or maybe utility. Okay. So, maximum current flows from here to here and maximum current flows from battery to the inverter or maybe some utilities, right. Now, we need to also learn the cables, because cable plays an important role in the functioning of a PV system, right. So, PV system usually contains DC and AC part, as you can understand. So, when we are talking about PV modules, okay, or arrays, so power generated here will be DC, then we will have, okay, battery we can write, and maybe inverter here, okay, then we will have AC. Okay. So, we need to know the cables used for this, and we need to know the cables used for this. Okay. So, that is how it is mentioned, PV systems usually contains DC and AC parts. For correctly installing a PV system, it is important to know the color convention. Okay. So, red is used for connecting the plus minus contacts of the different system components with each other, and black is used for interconnecting the negative contacts. Okay. And for AC wiring, so different color codes are used around the world. So, kind of color code used in European Union is different than the kind of color code used in other countries. Okay. In case of India and Pakistan, black is used for neutral and green is used for protective earth, and blue, red and yellow is used for phase. Okay. So, this kind of color conventions are used. So, now let us have a look about the cable losses. Okay. So, these cables have to be chosen such that resistive losses are minimal. Okay. So, in order to understand this, let us take an circuit which constitutes a supply voltage, okay, and then we have load, and then maybe cable resistance are included. Okay. So, RL represents the load having resistance RL, okay, and this R cable is the resistance of the cables, right. So, power loss at the cable can be calculated by using this equations. P cable is current multiplied by voltage drop. Okay. Since delta V cable is the voltage drop across the cable. Okay. This is the voltage drop across the cable. So, this can be calculated by using this, and this is something like V is equal to I into R, right, this summation of RL plus R cable. And then finally, what we would like to show is power of the cable which is dissipated is equal to I square into R cable, right. So, what we can say, so as the current doubles, then what happens, this power will be 4 times. Okay. So, what does it mean, as the current doubles, the 4 times as much heat will be dissipated at the cable, right. So, it is now obvious why modern modules have connected all the cells in series, because of these losses. Okay. Power dissipation is very high, because I square R losses will be there. Okay. So, we have to be very particular about the kind of cables to be used for this kind of standalone system. Okay. So, also we know this R cable is function of rho L by A, and also 1 by conductivity is L by A, right. So, this rho is nothing but resistivity, and also we can express in terms of conductivity. Okay. This is conductivity, right. Normally this L will be in meter and A is normally in millimeter. Okay. So, this block shows about values of this rho for copper and aluminum, because mostly copper and aluminum cables are used in applications. So, what will be the resistivity of copper? We can say 1.68 into 10 to the power of minus 8 ohm multiplied by meter. Okay. and you can see the values of copper for conductivity as well as resistivity and then conductivity for aluminum. Okay, because these values are given, as most of the times these values are used for calculation of this resistance of a cable. Okay, and usual thickness for cables are about 0.75 square millimeter, 1.5 square millimeter, 2.5 square millimeters, and so on. Okay. So, one very important observation is, since DC circuits are driven at lower voltages than AC currents, the currents are higher, requiring thicker cables. So, that you should keep in mind. For DC we need a thicker cables, right. Now, let us see the simple approach for designing an off-grid systems or standalone system. So, it includes the determination of total load current and operational time. Okay. Then determination of system losses. Then we need to determine solar irradiation in daily equivalent sun hours. It is also known as ESH, that is equivalent sun hours. And then we need to determine total solar array current requirements. And then we need to determine the optimum module arrangement for solar array, and then finally we need to determine the battery size for recommended reserve time. Okay. So, configurations are something like this. Okay. Modules are there, we have surge controller, then DC load, AC load, then we have inverter, and then batteries, right. So, this kind of configurations we are talking about. Okay. So, let us take a small example and try to understand the simple approach for designing a off-grid system. Okay. So, the example goes something like this: a 12-volt PV system, we are considering very basic PV system, has two DC appliances A and B. So, two DC appliances we are considering, maybe A and B, that may be anything, requiring 15 and 20 watt respectively. Okay. The average operational time per day is 6 hours for device A and 3 hours for device B, right. Maybe device A may be fans, or maybe tube lights, or device B may be mixer grinder, or maybe something like that. So, now the daily energy requirement will be, for device A is 15 watt multiplied by 6 hours. So, it will be 90 watt hour. For device B it is 20 watt multiplied by 3 hours, it will be 60 watt hour. So, these are DC appliances. Okay. We are not talking about the AC appliances, right. So, the total energy, daily energy requirement will be 90 watt hour plus 60 watt hour, it will be 150 watt hour. Okay. So, as we know, this rated voltage is 12 volt, then if we divide this total daily energy by 12 volt, then it will be 12.5 ampere hour. Okay. Now, next step is, for example, if we have AC load. Okay. So, maybe computer is one item and TV set is another item, okay, which are connected to the PV system. So, as you know, this will work in AC condition, means alternating current. So, we need to have inverter. Okay. So, if we consider an inverter, so in order to have AC, then we need inverter, okay, from DC. Okay. And we need to know what is the efficiency. Let us consider the efficiency of this inverter is 85%. Okay. So, under the condition, the daily energy requirement of the device expressed in DC ampere hour can be calculated. Okay. So, in this case, rated power of the computer is 40 watt and it will run for 12 hours per day, and for TV sets rated power is 60 watt and it will run for 3 hours per day. Okay. So, if we talk about computer, so 40 watt it will run for 2 hours, so it will be 80 watt hour. Okay. That is the AC requirement, and for TV it is 60 into 3, so 180 watt hour, right, and total it will be 260 watt hour. Okay. So, as we know this efficiency of the inverter, so what we can do, we can divide this, because we need to convert to DC, so we have to divide it. Okay. So, 260 divided by 0.85 will be 306 watt hour, right. So, if we divide this rated voltage, it will be 25.5 ampere hour. Okay. The next step, as per our design methodology, we need to add some kind of losses. Okay. This may be cable losses or any other losses which is encountered during operation. So, it is considered to be about 20 to 30%. So, if we consider 20%, so then what will happen? This DC requirement will increase by 1.2 times. So, it will be 45.6 ampere hour. So, now this all the things are DC, okay, and then we multiply by 1.2, it will be 45.6 ampere hour. Okay. Let us move to the next step. So, equivalent sun hours, if we consider a place in Guwahati, so it may be 4 hours. Okay. So, required total current generated by the solar array is total DC load to the ESH, okay, equivalent sun hour. So, equivalent sun hour is 4 and then total DC load is 45.6, then what we will get is a 11.4 ampere. Okay. Now, we are interested to know the number of modules to be connected in parallel. So, how to do that? If we consider a module having ISC value or rated current is 4.9 ampere, then we can divide this current, okay, that is no current generated by DC solar array. So, this is 11.4 divided by 4.9 is 2.32, which is equivalent to 3 numbers of the modules, okay, to be connected in parallel, right. The nominal voltage of the PV system is 12 volt and the nominal voltage of the module is also 12 volt. Here is the 12 volt for the module and then the PV system is also 12 volt. So, required number of modules to be connected in series is thus 12 volt by 12 volt is equal to 1 module, right. The total DC requirement for load plus the system losses are 45.6 ampere hour. The recommended reserve time capacity for Guwahati is said 2 days. Okay. So, battery capacity required by the system is, if we multiply this by 2, so it will be 91.2 ampere hour and minimum battery capacity for safe operation will be 114, because we know 80% capacity if we consider, then this divided by 91.2 ampere hour divided by 0.8 will give you this 114 ampere hour. Okay. So, if we consider 12 volt 90 ampere hour battery, then the number of batteries requirement will be approximately 2 numbers. Okay. That way we can do the calculations. So, we will be discussing detailed design methodology in the next class, okay, where we will understand the relationship between the kind of current goes from the battery to the inverter and then to the load, and everything will be considered, and we will study the clear cut steps for designing a complete standalone PV system. So, now let us summarize what we have discussed today about the different components of a standalone system like PV modules, surge controller, battery, inverter and load. We have not given more about the inverters, because we will be covering these things when we discuss the grid connected PV system. Okay. There are different kind of inverters are there, which inverter to be selected for what applications, that will be discussed. And also we have studied the loads. There are cases where DC loads are there, there are cases where AC load are also there. So, what we need to do in case of AC load and what we need to do in case of DC load, that we have discussed. Also we have discussed a design step for a standalone PV system, okay, and also we have discussed a small numerical exercise to strengthen your understanding of design of a standalone PV system. Okay. So, thank you very much for watching this video. Thank you.